Ever wondered how the transfer function for homogeneous tissue is numerically estimated? In the Tier 3 process, as outlined in ISO TS 10974, the transfer function is used to assess the safety of medical implants during MRI. One common approach to derive the transfer function involves applying piecewise excitation along the length of the implant, using a moving source, and measuring the response of the electric field near the implant tip. In this tutorial, we'll guide you through the simulations needed to calculate the transfer function numerically. Let's get started. We begin in the Sim4Life modeling environment by creating the numerical model of a standard active, implantable device. Initially, the core lead of the implant is modeled as a cylinder with a height of 635 millimeters. At the upper end, a second 4 mm cylinder of an extended radius is added to represent the tip electrode. The remaining part of the lead is then insulated by another cylinder of 1 mm radius. We continue by creating a wire block that will serve as our first plane wave source at the implant's tip. We then proceed to add consecutive plane wave sources along the length of the lead, with each one exciting a 10 mm section. To achieve this, we have two options. We can either manually clone and move the plane wave source by 10 mm each time, or we can use Python scripting in Sim4Life to speed up the process and minimize manual adjustments. The resulting electric field will be recorded at point 1 near the tip. We begin by creating a single-port FDTD simulation with a runtime of 12 periods. This duration ensures that the electromagnetic fields have sufficient time to fully evolve and reach convergence. Next, we head to the Materials section to create the material settings for the implant lead and tip, which will be modeled as perfect electrical conductors. The lead insulation will be defined as a dielectric material with a relative permittivity of 3. According to ISO TS 10974, the background material for the RF heating test should be modeled with a conductivity of 0.47 Siemens per meter and a dielectric constant of 78. We create a new plane wave source setting and set the operating frequency to 64 MHz, starting with the tip source. We create two manual grid settings, one for the lead and the insulation with a maximum grid step of 1 mm, and one more detailed for the tip of the implant with a 0.2 mm maximum grid step. To maintain consistency along the entire set of simulations, we create a common grid by dropping the PW sources folder into a new manual grid setting. Moving to the voxel settings, and to ensure that the lead is voxelized first, we assign a priority of 2. For the insulation, we assign a priority of 1, so it will be voxelized afterwards, forming a proper coating around the lead. To record the resulting electric field at the tip, we set point 1 as a point sensor. To create the remaining simulations for each source along the implant, we have two options. The first is to clone the simulation we just set up and then replace the source. For example, delete PW0 and drag and drop PW10. Next, clone this new simulation and replace PW10 with PW20, and so on. Alternatively, we can speed up this process using the Sim4Life scripting environment, which automates the cloning and source replacement. With all simulations set up, we use the batch voxel run to voxelize and run all simulations as a batch. Now that we have completed all the required simulations, it's time to gather the results and derive the numerical transfer function of the implant. We now move to Scripter to extract the complex scattered electric field component from the point sensor of each simulation. The total magnitude and phase components are normalized to the length of the implants in order to plot the transfer function. In power deposition assessments involving implants that extend from high to low conductivity tissues, the estimation of the transfer function inside a typical high permittivity medium might not be appropriate. Consider, for example, the path of a spinal cord stimulator. Part of the implant is embedded in cerebrospinal fluid tissue, while the remainder of the implant is primarily surrounded by fat tissue. In such a case, for the calculation of the transfer function, the above procedure could be repeated. This time, with the implant being placed in a homogeneous material with dielectric properties based on the length average properties of surrounding tissues. We now gather the results of the Tier 4- approach implemented within a homogeneous mixed medium. This approach is an intermediate step between the Tier 3 and Tier 4 procedures. In this tutorial, we've guided you through the numerical estimation of the transfer function for medical implants in Sim4Life environment. You are now able to simulate piecewise excitations and extract electric field data, putting you on the path toward effective Tier 3 and Tier 4- evaluations.